what about the backward probability case? Well, so two questions again here. At the very beginning, or I guess you could say, well, I think you'll agree that at time step t equals n, this is the form that we would write for the backward probability at time t equals n. So this may look somewhat mysterious. What on earth is that? And then, kind of related to the last question, can we get the total probability of the observation sequence from backward probability computation? I mean, we just did it a moment ago using forward probability calculation, but conceptual question: does the backward probability calculation also lend itself to being able to compute the total probability of the observations? Do you guys want to do this as a in-class question, or do you want me to just do it up front here? You guys want to do it as a question? Okay.
Is n plus 1 the next observation that you have? I don't.
Well.
I missed it. Did I miss it?
Well, so I mean, this question is deliberately being kind of simple-minded. All I did here was I took what we would write down. I mean, I think you'll agree there's nothing mysterious about this if I just replace my n by t. It's just the definition of the backward probability. So all I'm doing here is I'm saying, okay, what do we do? What is the meaning of the backward probability? And to be completely concrete, what number are we going to use, or what do we compute here at the very last time step when t equals n? Then the backward probability becomes that equation. What the heck is that? Because the backward calculation, I think you'll agree, it's intended to be computed backwards, starting from that one. That's the one at the end when t equals n, and we're going to compute it for t equals n minus 1 from that, and then we're going to compute it at t equals n minus 2 from what we computed at t equals n minus 1, and so on. So unless we are clear about what we mean by this, we don't have a starting point. So questions about what you're being asked here? Another way of phrasing this first part would just be, how do you begin the backward probability computation? We all, I think, know if we agree that if we had it at t equals n, the backward probability at t equals n, then you know how to compute it for all previous values of t. In other words, at t equals n minus 1, you'd compute it from t equals n, and so on and so forth, right? So all you're being asked here is, okay, how do we start the backwards probability calculation, which concretely is at time t equals n? Okay, well, if there are no questions, why don't you go ahead and think about that for a minute, and then enter whatever answer you come up with. So this first piece is actually trivially simple if you kind of get the idea. Formally, this has to represent an empty sequence because there aren't any observations after n. So saying the set of observations from n plus 1 to n, there are no such observations. So you can think of this as being like, what's the probability of the empty set? So by definition, that's 1. A more concrete way of seeing that same thing would just be to go back to what we were actually computing here So down here we had written out what the backwards probability summation would be. So if we had t to be equal to n minus 1, then we would be writing, let's say t is n minus 1, we'd be writing p of x from n to n given theta n minus 1 summation over theta n. So all you can see, I'm just plugging in n minus 1 for t here. Okay, so I think what you can see here is that the emission of the last observation has already been taken into account in this emission factor right here, right? There's the transition going from theta n minus 1 to theta n. And if we were to just write for ourselves what is this probability of, well, that's just xn, right? That's just the observation xn. So what's the probability of observation xn given theta n minus 1? Well, it's just equal, quite literally, to just that, right? There's the transition from theta n minus 1 to theta n, and there's the emission of xn given theta n, and then we're summing over theta n to get rid of theta n, right? So this equality will be true if this factor is just 1. Any questions about that? So you can think of this as one of two ways. One, the abstract version that says that the sequence xn plus 1 to n is an empty sequence, and the probability of an empty sequence is just 1. Or you can actually work out what it has to be based upon basic definitions, and again, you get 1. Any questions about that? Okay. So, moving on to the second part, we can indeed compute the total probability of the observations via the backwards probability calculation. We just need to be a little careful. So I think you'll agree that when t equals 1, that's our backward probability at t equals 1, right? Probability of all the observations from 2 to n given theta 1. So that's what we've got as the last piece of our backward probability calculation at time t equals 1. We want to get this. So we've got two problems, right? One is that we're missing observation x1, right? This only starts at 2. The second is we've got this theta 1 in there, and we don't want it over here. We got to get rid of it. So the usual logic applies. First, we need to also have x1, so the x1 is present just as well as all the other x observations. And then we want to get rid of theta 1. The only way to do that would be to multiply by the prior for theta 1. And now what we have is the joint probability for x going from 1 to n and theta 1. That joint probability, we can sum over all possible values of theta 1 and just get rid of theta 1, and it gives us just this, the probability of all the observations from 1 to n. Any questions about that?
Does that seem to say if it's x to n, like notation, not all of them. Like, you don't want like a one at the bottom.
Okay, so my apologies for my inconsistencies in notation. When the bottom index is 1, I'm just using as a shorthand. I'm not always explicitly writing 1. Probably I should have, just to keep it clear here. But if you see just this vector x in, it means all the observations up to n. My apologies for the notation. Other questions about this?
So I have in my notes that it says it's got the probability of theta t, the joint probability of theta t and x to the n over. So okay, sorry. So that equals theta t. That equals the forward times the backward.
Let's see.
Theta t and x to the n.
Right.
The forward times the backward.
I think I see what you're saying.
And then, so I have that theta t given x of n equal to that joint divided by x of n, x to the n. So in my answer, I included a denominator of theta 1 given x to the n. Does that make sense?
Let me see if I understand what you're saying. So you're saying something like p x n equal
Equals theta, probability of x of 1 given theta 1, probability of theta 1, probability of x to the n given theta 1 over probability of theta 1 given x.
you're gonna have to repeat that for me. I got the denominator. You said this, something like this.
Theta 1, yes, that's, and then the numerator.
And then the numerators are the joint.
So I'm just wondering, and then I just got that straight from like one of the things that we wrote down.
It sounds like you're saying this. Is that what you're saying?
No. Probability of, it's the answer probability of theta 1, probability of x over theta 1, probability of x
So this would be true, but we don't have this in the denominator. The denominator, that probability, we don't know it yet, right? And we've just done a backwards probability calculation. We don't necessarily know that. Going back to the slide, you're saying take this and divide it by...
Can I just show you?
Sure.
Sorry. With this. This
Theta
is equal to
two.
this. So then I just like,
Right.
so
Yeah. So what you've just given is equivalent to what I just put up on the screen a second ago. So you've written basically like this, except you have used t instead of 1.
well, yeah, because that's
I think the no, let's see. Okay, well, so you're using theta t. Okay, so you're using both a forward and a backward.
yes.
Right. Whereas the question was, can we get it from just the backward? So the answer is yes, you can get it from the forward and the backward, as you just said. That is correct. That is quite correct. You can compute the total probability observations from both the forward and the backward actually at any point t. You can certainly do that. And here, this is showing you how to get the total probability observations using simply the backward probability.
How can it be equivalent if one is the same and you divide by?
Well, the idea here is to get the probability of the observations, we're basically summing over all possible paths. So when we sum with the forward probability calculation, we are summing over all possible paths up to some point. When that point is the very end of the entire sequence, then we've summed over all possible paths over the whole sequence. So then that gives us this. When we do a backwards probability calculation, we're summing over all possible paths that start at a given point. When we move that starting point all the way to the beginning, then again, we can get the summation of the observation probability over all possible paths purely from a backwards probability computation. So it's just different ways of summing over all possible paths. You can do it forward, you can do it backwards, or you could do it both forward and backwards and meet in the middle, which was your proposal. All those are valid ways of summing over all possible paths. All right, why don't we take a 5-minute break?